Thank you for joining us today. My name is Sabrina Devone, and I will be the moderator for today's webinar. I am a member of our Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success, and this webinar series is an opportunity to showcase specific expertise or talk about new trends or code changes. Today's technical presentation is about distillation pressure control troubleshooting. Distillation pressure affects everything: vaporization, condensation, temperatures, and capacities. If the pressure jumps up and down, the column is unsteady, period. Pressure controls are among the most troublesome distillation controls. It is therefore important to understand how pressure controls work, and more so, what can cause them to misbehave. This webinar will survey some of the most popular pressure control schemes used, their strengths, their weaknesses, and common troubleshooting issues. So now I'd like to introduce our speaker, Henry Z. Kister. Henry is a highly recognized specialist with over 30 years of vast experience in all phases of distillation, including troubleshooting, operation, design, startup, and control. As a senior fellow and director of fractionation technology at Fluor, he designs, revamps, troubleshoots, and advises on distillation processes, equipment, and controls for the chemical, petrochemical, and oil industries. Henry is Fluor's representative on the Fractionation Research Institute Advisory Committee, serves on FRI's Design Practices Committee, and is a member of the U.S. National Engineering Academy. If you have a book or a section on distillation, most likely Henry is the author. He's the author of 3 textbooks, over 120 published articles on distillation, the distillation equipment section of Perry's Handbook, and the chapter on distillation in the Kirk-Othmer Encyclopedia of Chemical Technology. Many of his articles, as well as significant sections of his books, address distillation controls troubleshooting. Henry has conducted over 530 of the iChemie-sponsored practical distillation technology programs for major corporations in the US, Canada, and 24 other countries on 6 continents, and has recently started a new distillation control troubleshooting online webinar program offered by iChemie worldwide. Henry, please take it away.
Good morning, ladies and gentlemen, and welcome to the Fluor Innovation Builders Distillation Pressure Control Troubleshooting webinar. Before we get going, I want to make a couple of general comments. Very often when I give these presentations, people come up to me and they say to me, you know, we've got a column in our plant that does exactly the opposite from what you're telling us to do. It's doing everything wrong. It violates all the principles, all the beautiful principles that you're talking about, but it works. So what do you think we should do? Should we just tear that control system apart and use one of these beautiful control systems that you're about to show on the screen? Or should we just leave it alone? And whenever people ask me that question, my answer is, hell no, leave it alone. If it works, don't mess with it. The whole idea of this presentation is not to get you some ideas of how to tear out what works for you and replace it by something else. Quite the opposite. The idea, if you've got something that's working, it's good. Now, the idea of this presentation is that if you got something that doesn't work so good, maybe it will give you some ideas of what other people did to make it work better. And that's really the idea here. Now, the second thing that I want to mention, also a general comment, is that unlike trays or packings, that if you want to make a change for trays or packings, what you usually have to do is wait for the next turnaround so you can just open the tower, put a new distributor in or something like that. Not so with controls. With controls, you can try things out. If you come up with, if you all of a sudden latch onto some idea from that presentation or something, say, hey, that might be worth trying. Well, first of all, check that if you do that, it's going to be reversible. And if it's reversible, try it out. If it works, fantastic. If it doesn't work, go back to what you have. Okay, and with this general comments, let's get started and start off. As Sabrina told us before, pressure control is the most important control in distillation column, simply because pressure affects everything. It affects your vaporization, condensation, temperatures, the whole lot. If your pressure is unsteady, the whole column is unsteady, period. And because of that, we always control the pressure by manipulating the one variable to which it is most sensitive. Now that means that if you've got a vapor product, normally the good practice is to manipulate the column pressure by manipulating the product flow rate. On the other hand, if you've got a total condenser only making some liquid, then the usual way we control the pressure is by manipulating the condensation rate. And there's two ways of doing that. Either by flooding some of the condenser area, and this is called flooded condenser controls, or by manipulating the coolant rate. And we're going to talk about each and every one of them. We're going to start off and talk about the vapor product, which is only suitable when you've got a vapor product, obviously. Then we'll talk about when you've got only liquid products, and this is the flooded condensers and manipulating the coolant rates. And let's start with the vapor product. Here's the simplest method. What you do is you have a control valve in the vapor product rate. Now, if you want more pressure in the column, you close that valve. When you close that valve, you keep a lot of the vapor in the column, and when you keep more vapor in the column, its pressure goes up. Conversely, if you want to reduce the pressure in the column, you open the valve that lets some of the vapor out, and the column pressure goes down. Now, this method is suitable for pressure columns, for vacuum columns. With a vacuum, especially if you've got a vacuum pump. Now, if you've got an injector with a vacuum tower, very often we use an alternative, which instead of manipulating the vapor product rate, it manipulates the spillback around the ejector. Now, in many of our columns, the main product is liquid, but you still have a small amount of vapor vent stream coming out of the column. As long as you've got that vapor vent stream, you still control the pressure on the vapor vent stream. But in case you don't have enough vent gases, you can supplement it using nitrogen or fuel gas or some other inert gas that you put into the system. Now, all these three methods are good, fast, effective control methods as long as they are piped properly. Here's one that did not work. Now, this column is called a hot pot regenerator, very similar to an amine regenerator. And what they do is they've got an absorber that uses an alkaline solution to absorb H2S and CO2 out of a gas stream, just like an amine absorber does. In this case, it's hot potassium carbonate, which is an alkaline solution. It absorbs it, and then you send that rich solution into the regenerator, which is what you see out here, and you strip the H2S and CO2 and send them to the sulfur plant. Now, this is exactly what this column is doing, and so this is the overhead vapor, and the overhead vapor is the CO2 and H2S that are going into the sulfur plant. But this one did not work, and if you look at it closely, you will see exactly why it did not work. Okay, and if you're not sure, it's got this low leg out there, and you've got some atmospheric condensation or a bit of entrainment or something like that, and that will end up out here, will be trapped at the low point, and will start building up some liquid, which will back pressure the column. And that's why they could not keep a steady pressure in that column. And as it builds up, sooner or later, there's going to be enough push out there to get a good slug of liquid into the sulfur plant, which the sulfur plant will not appreciate. Okay, anyone knows how to solve that problem? Well, I'm sure many of you know. The idea is that control valve needs to be on a platform, not at grade. Now, anyone knows why people put this control valve at grade? I think many of you guessed it right. Accessibility. A lot of the time we work with a client, and the client will have a spec which will say all control valves shall be serviceable at ground level. a good engineering contractor needs to know when to take exceptions from client specs. We do that all the time. This is why clients pay us, so we can take these exceptions. And the contractor in this case, which of course was not Fluor, the contractor in this case should have told their client and said, look, we'll put all your other control valves at grade level, but not this one, because that one does not belong there. Okay, now this is one case. Now that low point can be even a lot more fun. And this is one case study that was published in the literature back in 1995. And I'll tell you one thing, even though it was published in the literature in 1995, I had a gentleman that came to one of my classes, and he swore to me that they had, once I described it, he says, hey, you're describing our plant experience. We had exactly the same thing. And the guy was a young guy, so he wasn't around in 1995, so it's obviously not the same case. But anyway, let me describe what happened there. Now, in this case, this is an FCC main fractionator, and for those who are not from the refinery, all it is, it's a fractionator, and the important thing that you need to know about it is that the overhead temperature of that is about 125 degrees C. That's all you need to know. Okay, and the way they control the pressure in this fractionator is by manipulating the steam valve that was driving the turbine that was driving the overhead compressor, wet gas compressor. Okay, now the way it works is if the pressure in the column became high, what it will do is it'll open the steam valve, which will speed up the turbine, which will speed up the compressor, and that will suck the gas out of the column. Vice versa, if the pressure fell in the fractionator, it will reduce the steam, slow down the turbine, slow down the compressor, and will keep the gas inside the column. The only problem with that is that you can only slow the turbine so much. If you slow the turbine too much, you're going to lose the compressor. So for this situation, they had a split range pressure control. So if the pressure went, if you slow down the turbine to the limit, the next thing will happen is it will open this valve out here and send some hot gas from the compressor discharge back into the column, and keep the pressure up that way. Okay, the only trouble here, again, you've got that low point, just like we had in the last case. But here the situation is a lot worse, because in this case, throughout the whole summer, there was no need to use that bypass. There was always, the pressure never fell low enough so that you need to use that bypass. So that valve was shut throughout the whole summer. Now, picture what's going to happen in this line when the valve is all shut. This line is a vapor line, but it's sitting out there like a dead leg, and under atmospheric condensation, you've got vapor that's going to condense and build up in that case. Now, let's think about what is going to condense. And I need to tell you one more thing, and this is that the overhead from the drum is saturated for hydrocarbons, but is also saturated for water. So what will condense in that line is both hydrocarbons and water. Now, after a while, the hydrocarbons will float on the water, and what will stay in the leg is a leg of water. And it will sit there. It's not going to bother anyone until next winter. Comes next winter. One cold day, the pressure drops in the fractionator. It slows down the turbine, slows it as much as it can. The next thing it's going to do is open this valve and try to put some hot gas from the compressor discharge into the column. But does it put the hot gas into the column? No. What does it put instead? A cold leg of water, right? And so you've got the top of the fractionator sitting at 125 degrees C, and you're dumping into it a leg of water. This is all hydrocarbons here. You dump a leg of water in there, it will vaporize in an instant, and the pressure will surge. Now, these guys were lucky. They had a good relief valve that lifted within 20 seconds. And if it didn't lift that fast, they could have overpressured the column and blown themselves up. So they were lucky. And same thing with that gentleman that came to my seminar. The same thing. He had also. They were lucky to have this good relief valve. But they still had some fun. The compressor surge, stuff like that. But at least they stayed alive. So again. Now, I've seen the same system out here too. I've seen that quite a few times. I've never seen anything as spectacular as what described in that case study, and also by the gentleman that came to my seminars. But I've seen a situation in which every time they opened that valve after a period that was closed, they got a nice bump in the system. So again, the lesson of that: avoid these low legs. Now, in some situations, especially with these compressors, you might not be able to avoid them. If you can't avoid them, at least put some kind of a pumping trap or some kind of like a steam trap device that will take the liquid out. Make sure the liquid is fully drained before that valve opens in the next winter. Okay, now this really sums up all the methods I want to talk about when it comes to vapor products. And really the big lesson is avoid these low legs. And every time you've got vapor lines which are involved with the pressure control system, avoid any pockets. And if you've got to have pockets, make sure that there's means of making sure that there's no liquid accumulating in them. Okay, so we're going to move to liquid products. And as we said, there's two main methods that we use when you got liquid products, and one of them is the flooded condenser. And let me talk about that first. Now, incidentally, you see a lot of page numbers out there. Now, these page numbers refer to a couple of my books. DO stands for distillation operation. So if you want to read more about that, you will find it in distillation operation on page 530. Sometimes you see DT, the T stands for troubleshooting. That's another book, Distillation Troubleshooting, the page number, so it'll tell you where to look it up. In addition to that, when it comes to flooded condensers, there's an article that we wrote right on flooded condensers, and this article is referred to at the bottom out here. Okay, now there's a lot of variations of this flooded condenser control scheme. And I'm going to start off with probably the most common variation, and the one that is really the basic variation of that. Now, what we do in this case is we insert a control valve in the condensate line from the condenser to the drum. And what we do is we keep a liquid level inside of that condenser. We flood some of the condenser area. Now, the flooded area does not do condensation. It does heat transfer. It subcools the liquid, but it does not condense. The only area that does the condensation is this red area out here. This is the only one that does the condensation. Now, when we open the valve, when we open the valve, we lower the amount of liquid in the condenser. We reduce the flooded area, which means it gains us more red area, more condensation area. You get more condensation, pressure goes down. Vice versa, if you want to increase the pressure, you close that valve. When you close the valve, you raise the liquid level, you reduce the condensation area, there's less condensation, pressure goes up. That's how it works. Now, don't forget the equalizing line, because if you don't have an equalizing line, you can't control the pressure in the drum. And that equalizing line needs to be well-sized. And people say to me, what do you mean by well-sized? Believe it or not, the key to sizing the line is not that line. The key to sizing the line is this line, the condensate line. And the good practice is to bring that condensate line right there near the bottom of the drum. A few inches so that it can get out, okay, but near the bottom of the drum, without any slots, without any large holes out there. People very often put some holes in there, they say for siphon breaking or just in case there's some vapor that it will disengage and all that. Okay, if you really have to put a hole in there, make it small. No more than ½ an inch, ideally even less than that. But no more than that. Slots is not what you want. Now, the main problem is, let's say if you didn't have a slot, you just took this condensate and you splashed it into the vapor space. Now that condensate is subcooled. You splash it into the vapor space and you're going to condense the vapor in the drum, generate a vacuum, which will suck tons of vapor through the equalizing line. And then you need a huge equalizing line to do that. And if the equalizing line is not huge, you can end up with vacuum in the drum. And people have done that. And that's not what you want to happen. Okay, so because of that, again, bring it near the bottom. Now, what about the slots? Well, with the slots, it's the same type of thing, right? Okay, you've got a slot out, a big slot out there or a big hole out there, and it will squirt this cold liquid into the drum, into the vapor space. And when it does that, again, it will condense the vapor, and it will suck a lot of gas, a lot of vapor through the equalizing line, and you need a very large equalizing line. Now, this is if you're lucky. Now, what happens if you're not lucky? Well, if you get a nice, good subcool inlet, the vapor pressure of the liquid can be very low, well below that one of the drum. So instead of the liquid coming out, that low vapor pressure will actually suck the vapor in. So now the vapor is going to come in. And this is a dew point vapor, and you're contacting it with subcooled liquid. And that, when it does that, it will hammer, bam, 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 bam. That's what it does. And in fact, I want, and there's been, we're having these distillation symposia every odd numbered year. So the next one, 2021. In 2017, we had a distillation symposium in San Antonio, Texas. And in it, the Valero distillation expert, Daryl Hansen, gave a beautiful presentation. It's one of the best we've ever had. And in this one, he described exactly that kind of scenario. And to describe that scenario, what he did is he got his cell phone, put it in a video mode, and hooked it onto a thermal camera. And he actually shot a thermal video of this line. And you could see that line going red and blue and red and blue. You could almost feel the vibrations as you were watching this video. This was fantastic. Really got you a good flavor to what is happening here. And we presented a paper at that time together with Holy Frontier on a very similar incident that happened to us. We didn't have this beautiful video that Daryl had, but what we did is in our case, it was a lot more violent. What happened is we had these bam, bam, bam caused some handles to fly off the of valves. We had a thermocouple that was breaking. We had a flange that got loose, and the client actually, after they had that experience, and incidentally again, that column was not designed by us, and after they had the experience, they shut the whole unit down. They said, this is too much safety. We don't want to compromise safety here, and we're not going to go back online until we fix the safety problem. And we had the pleasure of fixing it. And all we did is we closed that slot. That's all we did. Once it was, everything came good. So beware of oversized slots or oversized openings of that line. Okay, and here's a picture of one of these flooded condensers. You can see it out here. You can see it's nice and warm. This is where the vapor is. And out here, you can see this is liquid. So that's exactly how it works. Okay, back to the basic scheme. As I mentioned to you before, all these flooded condenser schemes are only suitable for total condensers. In other words, where you've got no vapor product. But here in California, we've got a law, which is called Murphy's Law. Incidentally, for those of you who do not know, Murphy was a Californian, and he was an engineer too. Okay, and Murphy's Law tells you that every time you're dealing with a total condenser that only has liquid product, there's going to be some times in which you'll have non-condensables. Now, if you get non-condensables getting into these condensers, they ain't going to go down through that line. And so you've got to get them out. And the only way to get them out is by using a vent. And so, yes, we do need a vent in this case. And you can vent it to the drum, you can vent it to your fuel gas, you can vent it to the flare, you can vent wherever you like, but you do need to have a vent. Now, if it's only something that happens during startup and shutdowns and something like that, a manual vent is plenty good. On the other hand, if you've got some problems with the upstream column and very often you get some lights that come into there and need venting, you may want to use an automatic vent. But whatever it is, you do need a vent. Okay, now going to some variations of that scheme. Sometimes people ask, do you really need the vapor space in the drum? The answer is no. The only thing that the vapor space buys you is search for the product. Do you need the drum at all? No. The only thing that the drum buys you is search for the product and search for the pump. And if you don't have a pump, and very often in specialty chemicals, you don't have a pump, you've got all this, the condenser is above the column and there's no need for a pump, then you don't need to have the drum either. That saves money. But in most petrochemicals and refining, we do have a pump, so we do need at least the search for the pump. But we don't always need the search for the product. So we can go to this next method called the flooded drum. Now, this is a project manager's favorite because the drum is about half the size. And it's not just the drum, but you've got to have platform to hold it and all that, and piping and all this. And out here, also, you eliminate the level control too, because if the drum is full of liquid, there's no need for level control. And this is called the flooded drum method. Okay, now let's see how it works. Okay, if you want more pressure in the column, you close that valve. When you close that valve, you raise the liquid level in the condenser, and it reduces the condensation area, pressure goes up. Conversely, if you want to reduce the pressure, you open the valve. When you do that, is you lower the liquid level out here, and you got more condensation area, pressure goes down. And it responds quite fast to operations people like it too. 3 problems with this method. Number 1, remember what we said before. Pressure is the most important control in a column. Pressure is boss. Pressure tells valve to open, valve opens. Pressure tells valve to close, valve closes. Valve does not argue, and it does it fast. And if you ever look at the flow meter on the product line, it never draws straight lines. It jumps all over the map, which is fine if you go into storage. Not so fine if you've got a downstream unit. So really what we're saying is the only time that you even want to think about using this method is when your product goes to storage. Second issue. Now, we said we need a vent out here to vent the non-condensables, but some non-condensables can still be dissolved in the liquid, and then they decide to release themselves in the drum. So you need a drum on the vent too. You need a vent on the drum too. But this venting is a lot more complicated because you're venting from near the top of a liquid full drum. Now, the minute you open the valve, you're not gonna get just vapor, but you're gonna get some liquid and train with it, which means that you need the only place you can send it to is some system that can handle the liquid, some kind of a knockout drum. You can't send it to a firebox or something like that. Okay, and also you need to think, if it's at the lower pressure, that liquid can flash over that valve, and as it flashes, it chills, and as it chills, it can go below the safe working temperature of the line and of the valve. So again, that all need to be considered. So the second thing is, again, and you can again vent it manually, vent it automatically, all these things, but you do need to consider, okay, what can you vent it, and where do you vent it to? Last but not least, and this is becoming the major consideration these days, the minute you lose that pump, you've got yourself a relief. And this is because once the pump is gone, that liquid level will climb very quickly in the condenser, eliminate all the condensation area, and the pressure will just shoot right up. Next thing is the relief valve pops. And this is something that we don't like to do these days. And in fact, if you go back 20 or 30 years, there's a lot of systems like that. These days, clients shy away from that because of that relief concern. And in fact, we're familiar with one case in which a client completely bought themselves a new drum, twice the size, to give themselves the vapor space because they had a relief incident they did not want to see that happen again. Okay, so because of that, we're seeing less and less of these systems these days. And you might say to me, well, wouldn't the same thing happen with the other system? Okay, here's the other system. Would the same thing happen in the other system? The answer, it would, but only after that liquid fills the drum. Because until then, say you lose the pump, it'll just take a while to fill the drum, typically about 5 minutes. And 5 minutes is plenty of time for the operator to do something. The other one happens in less than a minute, and there's not enough time for the operator to do it. Okay, now I want to look at another aspect of this of condensers controls, and this is the pressure balance. Okay, now for start, out here we've got this two. This is one point in which the two routes are together. There are the bypass and the main route to the condenser, and the same next place where they come together is the drum. So let's call it P1 and P2. Okay, and Now, P1 normally will be the same as P2. This is a pressure equalizing line, so these two will be the same. So at least out here, there's no pressure drop. Now, let's look at the pressure balance in the other route. And the pressure balance is what the driving force is the liquid head difference between the liquid level in the condenser and the liquid level in the drum. Right. Now, the resistance to it is the pressure drop in the valve plus the pressure drop in the condenser. Okay, and we can write it in a nice little equation here, and it tells you that for that head is going to be equal to that pressure drop plus this pressure drop. Now, that means that if you got a high pressure drop in the condenser, you may not have enough head to push the liquid down, which will bottleneck your capacity. Okay, to overcome that, what people do is they put a valve in here. And so now that gives you a bit more pressure drop that you can play with, and it essentially helps the liquid head that you've got out here. Only question is, how are you going to control that valve? And conventional wisdom is to use a DP. And you'll see, usually they put a DP out there. Okay, only one problem with that. Those of you that follow the literature on the subject could have seen a paper that came out about 12 years ago by one of the experts in the field, a guy called Zach Friedman. And what Friedman is saying is that he's seen this method more than 100 times and he's never seen it to work. And he's got a good argument why it doesn't work too. And he says basically the pressure control and the DPC fight each other. Okay, let's see why. Okay, let's say the pressure in the column rises and you try to reduce it. So the pressure in the column rises. What it will try to do here is open the valve, right? Open the valve to give you more condensation area and generate a flow downwards through that line. Now, also when the pressure goes up, the DP goes up. And to reduce the DP, what will it do? Open this valve and sends more vapor out here, which will go backwards through there and fight the first control action. Now, Friedman presents three solutions to that. The first two I'm not too excited about, but the third one is actually quite a good one. And I'll mention that in a minute. Okay, but anyway, he says that he's never seen it to work. Well, I can't say that I've seen it 100 times. Okay, I've seen it maybe 10 or 20 times. And most of the time it did work. But I thought, okay, well, I'll take it seriously what he's saying. And I thought, hey, I've got people coming to my classes. Ask them the question, do you have this control system? And if they said yes, does it work? And I was getting, basically I was polling about 80% of the people said it does work, 20% said it did not work. Okay, so then I've turned to the people that say it didn't work. Well, I said to them, if it doesn't work, what do you do? And they say, oh, we just put a DPC on manual. Which actually makes very good sense. Because there's no need for tight control on that valve. The only reason why we have that valve is to give ourselves pressure drop so we can get the flow forward through that route. So you can actually just have it almost throttle or manual and you'll be fine. And that's exactly what they're doing. And actually, one time that I had that discussion, I had one guy from the other group that said that it does work. And he jumped in, he says, oh, in our case, well, we don't put it on manual, but we slow it right down. Slowing it right down is putting it on manual. And actually, the good solution that I think from Friedman on that I like, the one solution I did like, is he was saying that instead of controlling the DP from the process variable on the PC, he controls it from the set point on the PC. Semi-manual. So again, if you've got a system like that and it gives you grief in automatic, slow it down, put it in manual, use Friedman's idea of using it from the set point. These are all possibly good solutions. Okay, one more aspect. Now, in many of these systems that we have, some of the stuff that condenses is water, usually a small amount, and you don't want to reflux the water back into the column because it can cause corrosion. And to do that, you include a device called a boot. Now, the idea is that boot collects the water that flows on the floor, runs it out there, and then you've got a control valve and you take it out, you take the water out. Now, if you've got a boot out there, it needs to be properly configured. And here and really the idea is you bring the liquid in at one end and the boot's got to be at the other end, because you need some settling time for the water to get out of the hydrocarbons, or out of the organic, which is insoluble in whatever it is. It needs some time to get in there. So that boot needs to be at the other end. And the reflux line needs to come on the other side of the boot. Because, and I'll tell you, and I've seen people with the reflux line coming out here on this side of the boot, and they wondered why the reflux got water in it. I mean, the reflux, if it's ahead of the boot, it's going to take the water before the boot does. Okay, so again, it needs to be properly configured, and that's got to be at the other end. And some people actually stick that line about something like 6 inches above the floor of the drum, and that's fine. That's good stuff. Okay, but whatever it is, this is something that needs to be properly configured. Okay, gonna move on. And in many systems, instead of having the valve in the condensate line, which I've shown in the last few slides, they put the control valve at the vapor line to the condenser. And this is actually something that many of the major licensors like to do. And very often they use that control system. Now, this control system is actually, from a control point of view, it's a beautiful control system. It actually augments the control action that we took by flooding the condenser, which is what we talked about, by another mechanism. And the other mechanism is adjusting the pressure, the condensing pressure out here. Now, again, if you want more pressure in the column, that means you want to condense less. And to condense less, what you can do is close the valve. Now, that closing the valve raises the liquid level there, which helps you. But also, closing the valve reduces the condensation pressure, which reduces the condensation temperature, which reduces the delta T. So that's an additional one. And in a condenser, they work together. In a reboiler, not so much. In a reboiler, they might tend to fight each other. But in a condenser, they do not. They tend to be augment each other quite nicely, work nicely. Another advantage of that is by doing that, by condensing at a lower pressure out here, you also reduce subcooling, which sometimes subcooling is desirable, especially if there's NPSH problems in the pump. In other cases, subcooling is not desirable. And if it's not desirable, that system, again, offers some benefits. Okay, what are the disadvantages? Well, there's two disadvantages. For start, a valve in the vapor line is much bigger than a valve in the liquid line. Capital. The second thing, you're condensing at a lower pressure, which means you're really running the column at a higher pressure than you need to. The other method just essentially runs the column at the same pressure that you need for condensation. Here, you run the column at a higher pressure than you need for condensation. Now, that means that with a higher pressure, you lose relative volatility. And when you lose relative volatility, you need to use more reflux and more reboil. Operating costs. And this could be quite expensive. So this method is more expensive, both from capital, and also the condenser tends to be bigger because of that. So this method costs you more, both in capital and in energy. But as we said, as a control method, it's quite nice. Now, if you got this method, there's one watch out. And the watch out is you don't want that valve to close. And just picture a scenario when something like that happens. And let's say this is winter time and the column is operating at low rates. Winter time, cooling water is cold. So that condenser is a real big and strong and powerful because it's winter time. Okay. And one cold day, the pressure in the column falls, and to try to bring the pressure back up, it closes the valve. And you just hope that it's not going to close it completely. Because picture the scenario of what happens when it closes completely. You got a few miserable cubic feet of condensable vapor in that condenser. And you've got a big, powerful condenser. Cooling water is cold. It's not a challenge for that cold cooling water to condense these few miserable cubic feet. And it does it in an instant. And as soon as it does that, you've got vacuum right there. And when you get that vacuum, it sucks liquid from the reflux drum, and that liquid comes out rushing, bang! People have ruptured lines with that mechanism. Fortunately, it doesn't happen too often, but it does happen. It hammers like crazy, and you definitely don't want to be there when it happens. And the one time you want a valve to leak, It does not. Okay, so if you got a system like that, always look at the possibility. Can that valve fully close? And if the answer is yes, find some way of making sure that it doesn't. Valve limiter, bypass around it. There's a lot of solutions. But whatever it is, don't allow that valve to fully close. That's the lesson. Okay. Well, time to get to one of the all-time favorites, a hot vapor bypass. Now, this is when it comes to pressure control systems. We've done a survey some times ago, and in that survey, we found out that when it comes to pressure control systems, this is the most troublesome pressure control system. And incidentally, most of the principles of that method have been in the literature for more than 60 years, proudly put out by Fluor. Fluor were the first people that actually addressed how this method works. We had a guy by the name of Whistler that used to work for us about 60 years ago, and he was the first person to write a paper on how the method works. Now, 3 years after Whistler came a guy from Exxon by the name of Hollander, and he filled in the blanks. So whatever Whistler did not discuss, Hollander did. And between them, they covered the field real good. But even though these two guys cover the field real good, we're still finding new things about it. And we're still learning new things. Some of you could have seen a paper that we put out on hot vapor bypass together with this gentleman I mentioned before, Daryl Hansen, who's the distillation expert in Valero. And we learn new things in this exercise, which I'll mention very shortly. Okay, so we're still learning new things, but whatever it is, it's potentially very troublesome. Okay, now let's see how it works. And the very first thing that catches your eye is that this condenser is below the drum. And you might say, why do we put condensers below the drum? And the answer to that is, well, you wouldn't think that this is something really worthwhile to do if your exchanger is a tiny little heat exchanger or something. But if your exchanger is 5 feet in diameter and 20 feet long, and there's 4 shells and tubes that do the same thing, big advantage of putting them at ground level and not building a platform for them. Because remember, if your condenser is 20 feet long, the platform needs to be 50 feet long because you're going to pull the tubes at the turnaround. And it makes a lot of good sense to put it at ground level when you're dealing with big time equipment than to put it up high. Okay, so we condense it at ground level, then we pump it into the drum. But there's no pump. So how does that liquid get into the drum? And when I ask people, they usually say to me, by pressure. That's partially correct. The full correct answer is vapor pressure. Now, realize this one thing. That liquid that comes out of the exchanger is subcooled. When it's subcooled, what happens to its vapor pressure? Vapor pressure falls big time. Here are some applications, and you can see how big time. And let's just pick the middle one. 1 degree F, subcooling, reduces the vapor pressure in a debutanizer by 1.5 psi. And this can lift the liquid up 7 feet. Now, this 1 degree subcool, we're usually talking about something like 30, 40 degrees subcool. A 40 degree subcool will lift the liquid up to 300 feet, almost 300 feet. We don't want to lift it up to 400 feet. We want to lift it up to the condenser. Okay, so to the drum rather. So really, now forget about the bypass for a minute. Let's say there's no bypass. So this liquid in the condenser, the top of that, the surface here, is at the condensing temperature. Okay, the vapor condensing temperature. But the liquid here is subcooled, so the vapor pressure in the drum is that of the subcooled liquid. And that means that it can push it up 280 feet. You can put the drum that far high in the air. And if the drum is only 15 feet above you, it will push the liquid right to the top. And we don't want to do that. But to avoid that, what we do is we bleed some hot vapor. And that hot vapor heats up the surface. Now, the vapor pressure in the drum does not care what happens in the bulk liquid. It cares about what happens in the surface. And as long as you keep the surface hot, then or fairly warm, then you can do whatever lifting you want. And that's the idea. And so what we do is we manipulate the amount of hot vapor to essentially control the level of liquid in that exchanger. Okay, so this is a flooded condenser method, just like all the others. Again, so if you want more pressure in the column, the whole idea is you need to increase that liquid level there, right? Increase the liquid level. To increase the liquid level there, you open the valve, sends more hot vapor, which heats up the surface. It heats up the surface, then the vapor pressure of that liquid goes up, the pressure in the drum goes up, and it sends liquid to the condenser. Conversely, if you want to reduce the pressure in the column, what you need to do is you need to close that valve. You have less hot vapor. And when you have less hot vapor, then the surface temperature falls off. When it falls off, it gets lower pressure in the drum, and it sucks liquid from the condenser into the drum, and then increases the condensation area. That's how it works. Now, let's focus a bit more on the heat balance that we've got out there. Now, there's actually three factors when it comes to the heat. The first one is there's going to be a heat transfer from the bulk liquid to the surface. Now, this is essentially by a conduction mechanism. Very small amount of heat is being transferred, and this is because processed liquids are excellent thermal insulators. And if you don't believe it, next time when you run your simulation, ICES, Pro 2, whatever, take a look at the thermal conductivity of your processed liquid. And after you jot it down, pick up a copy of Perry's handbook and look up the thermal conductivity of asbestos, which we know is the best insulator that we have. And what you're going to find is that the thermal conductivity of a processed liquid is typically about 2-3 times that of asbestos. So it's not as good an insulator as asbestos, but it's not that far behind. And so the whole thermal gradient happens over 6 inches out there, and the rest of the liquid stays cold. And so that mechanism of moving is essentially heat going through an insulator, which is very little amount and very steady. You can change the subcooled temperature as much as you want, and it's not going to affect the motion too much. The second factor is ambient losses, which will vary between a calm day and a windy day and a rainy day. But again, they're not all that much. The main drive is that vapor. Now you've got vapor condensing onto a surface. Now, you may remember from university, right? Condensation, heat transfer. It's a huge heat transfer coefficient, and it happens fast. So really, this is the driver. Whatever that guy does, that is the main driver that we do have. And that's exactly the way the method works. So it's a very responsive. So people that have it and have it working properly, it works really nice. Okay, so with all this explanation, then you might ask the question, well, in that case, why are you saying that it is troublesome? Reason for that is, again, if you follow the explanation, you could have noticed a very strong dependence on the surface. Everything here happens on the surface. And for that method to work, the surface needs to be steady. Now, what can cause unsteadiness? Well, take a look. You got a vapor line blowing straight onto that. Hey, after this webinar, get yourself a glass of water, right? Get your mouth close to it and go and blow onto it. See what happens. See what happens to the surface. Okay, don't do it with coffee. Okay, that's what's going to happen. So this is one thing that can ruffle the surface and completely drive that method crazy. Another thing is that liquid jet. Now you think, oh, liquid jet, wouldn't that disperse? It doesn't. Liquid jet goes straight up. And we know that it can go through about a few feet of liquid without any problem and get to the surface. And that can pump subcooled liquid onto the surface. And in fact, in the article that we wrote with Daryl Hanson that I mentioned, in this case, we were really doing a post-mortem of an instability event that Valero fixed. And in that one, what happened is you had liquid out there, and it came in about 5.5 feet per second, which is a little bit on the high side, but not out of range. It's a reasonable number. And it came in, that liquid was at 66 degrees. And you had the vapor out there was at 125 degrees. Now, what it did is that, and there was a bit of a disturbance because there was a bit of rain in the area, so there was a bit of a disturbance. And and it caused a bit of a bit more condensation, which means that liquid rate went up. And when it went up to about from 5.5 to about 7 feet per second, when it did that, it pumped out some of that 66 degrees onto the surface. Now, as soon as you did that, it immediately condensed some of the vapor, dropped the pressure out here. As soon as it dropped the pressure, it sucked more liquid from the condenser, which again pumped it more to the surface, which got colder and pumped more liquid from the condenser and got colder. And within 5 minutes, they transferred about 10 tons of liquid from the condenser to the drum. Now, this was a mild upset. They had upsets which were a lot worse than that. But it just shows you what it can do. And the hot vapor bypass could not catch up with it. It happened so fast. Now, the way they fixed it is by throttling this valve out here. They had a valve and they throttled it out here. And once they did that, they at least slowed that suction movement that keeps on sucking more and more, and that solved the problem. Once we understood the problem out there, we kind of learned a bit about the design. For start, the throttling valve is invaluable, as they found out. Another thing that can help is some kind of a baffle out here to stop that jet coming to the surface. In many other cases, that is the solution, especially when the problem is the vapor line, and make sure that it does not impinge on the liquid. Now, this is one system you don't want to have. Ladies and gentlemen, this is not one system that didn't work. That's 24 systems that I've been involved with in one way or another that did not work. And if you look at it, you might just ask the question, how on earth can something like that work? If you understood the principles of hot vapor bypass, there's just no way on earth that it will work. Because what you're doing here is you're taking this hot vapor and collapsing it onto the subcooled liquid. All this, remember all this lift and stuff like that? Look at that. And it hammers too. Bam, 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 bam. Okay. So again, in one of the instances that I was involved with, the client was saying to me, well, okay, fair enough. We've got a nozzle out there, so we can take that line, put it in the nozzle, but he still wanted to splash the liquid onto the surface. I said, look, that's not gonna, well, it did not work. It made things a bit better, but not much. Next turnaround, he also took the line and extended it below the liquid surface with the vapor line going out here. That did work. Okay, I think we've had enough of these of all these flooded condensers, and I just want to skip a couple of slides there and get into the coolant variation. Okay, now here's one more method. This is in which we vary the coolant rate. In this case, we've got the pressure control controlling the cooling water. From a control point of view, it works nicely. Pretty straightforward. You want more pressure in the column, you reduce the cooling water. Want less pressure, you increase the cooling water. Okay, 3 problems with it. Number 1, the minute you close that valve, you reduce the velocity in the cooling water tubes, which gives you accelerated fouling and accelerated corrosion. Number 2, when you close that valve, you increase the temperature, the outlet temperature in the cooling water, which again reduces which increases your fouling and increases your corrosion. And number 3, control valves that people use in cooling water are usually butterflies. Butterflies are very often oversized, and you end up with controlling between 5% and 7% open. Okay, but other than that, it's good. Okay, but sometimes, and you might say, okay, well, this is our last choice. We don't want to use that. Sometimes you don't have a choice. Sometimes you've got to use it. Not so much for pressure control, but for temperature control. Now, we already mentioned the situation in which we've got the main product that we've got is liquid, and there's also a bit of vent gas out there. Okay, well, normally we can just have the cooling water going flat out, but there's some situations where we cannot. For example, was in one situation like that in an ethanol column. So they had ethanol out there, that was the liquid product, and they also had some carbon dioxide, which they were venting out here. Now, if the temperature gets too cold, the carbon dioxide gets absorbed in the ethanol, gets the ethanol off spec. So you can't have that, so you need to keep the temperature warmer. You don't want it too warm, because if you have it too warm, you end up with ethanol going into the vent gas. You don't want that either. So you really need to do a temperature control. The only problem is you run out of levers to pull. So the only lever you've got available is that. And that's why you need to do it. As I said, not so much for pressure control, but mainly for temperature control. Now that can generate another problem, and I want to demonstrate it with the next case. This is one that's been published a long time ago. And in this case, this is something that happens. And the unique thing about it is the column overhead temperature was 120 degrees C. Okay, again, in this case, the drum was vented into an atmospheric header. So really, it was pressure control, but pressure control without a valve, because it was riding on the pressure in the vent header. So essentially, that's the pressure control there. And again, they had the same situation. They did not want to absorb any of these inerts into the liquid product, and at the same time did not want to lose too much liquid product. So that the temperature control, the only place they could do it is on this. Now, just imagine one day, for some reason, the temperature fell. When temperature falls, it closes the valve. And if it closes the valve too much, you got 120 degrees C vapor boiling that water. And the water started boiling. Once you start boiling water out there, essentially it's a cooling water failure. Now, lucky enough, they managed to shut it down quickly enough before they lifted the relief valve. But nevertheless, that's an issue. And some of you could have seen there's a paper that came out about 2011 by a guy called Jacques Demerui from Sasol. And it was a classic. I mean, one thing that was in his favor is he didn't have cooling water, but he had condensate, okay, steam condensate. And again, they were struggling to make sure that they don't boil dead. They had all sorts of interlocks and things like that. And these guys were really had a lot of problem with this. Okay. Now, if you got air cooler, life is a lot easier. Okay, because out here you can control the pressure or the temperature, and again, more for temperature than pressure by the if you got a variable speed fan, by the speed of the motor or the pitch of the blades otherwise. And these are good and effective methods, except they might get a bit of a bump every time you get a thunderstorm or something like that, but people live with it. If you've got refrigeration, changing the coolant is the standard way of doing it. Now, in this case, if you want to you essentially control the refrigerant level in that kettle. So if you want to get more pressure, you lower the level of refrigerant in the kettle, which cuts back on the refrigerant flow. And as a result, you get less condensation. If you want to condense more, in other words, to lower the pressure in the column, you raise the level, you open the valve, raise the level, more refrigerant, and the pressure goes down. Again, very straightforward, a bit slow, but energy efficient. And because of that, whenever you see refrigerated columns, almost always you use this method. Okay, and one more method I do want to mention. Now, back to the cooling water. One thing with the cooling water we mentioned before is that the low velocities cause the fouling and the corrosion. And that is a bigger factor than the warmer temperatures. And one way of overcoming that is by using a booster pump, just like that. Okay, so what happens is you recycle some of the cooling water, you recycle it back into the exchangers. You always keep the velocities up high. And this is kind of nice. And now there's lots of variations of this method. The one I'm showing here is my favorite and became favorite after I was taught that by a gentleman called Richardson that used to be the control expert for Union Carbide in the old days when we had Union Carbide. And the reason why it was his favorite and became mine at that time is because if you lose this pump, you still got cooling water going through the exchanger. Now, to make that happen, that check valve needs to work. And so you need to test it regularly, make sure that that thing works. And the idea of that is that because if it doesn't work and your pump fails, then the cooling water can bypass through there and go into the cooling water return, and you basically not gain its benefits. Now, one other big plus of this scheme is that it enables you to keep the cooling water warm even during the days of the cold winter. And the days of the cold winter could be a problem when some of the components in the overhead product have got a high freezing point. So this one prevents it from freezing. And so whenever you're dealing with components that can freeze on you, this method is definitely favored. Okay, one more method here. Now, until now, we talked about keeping a tight pressure control in the column. We said how important it is. For the very last slide, I'm going to turn the tables. I'm going to talk about floating pressure. Floating pressure. Why would somebody want to float the pressure? And the reason for that is that a lot of the time, really, what determines the pressure in the column is the air or the cooling water. Well, the air and the cooling water are hot during summer, but they're cold during wintertime. So during wintertime, you can operate at a lower pressure. If you can operate at a lower pressure, you can reduce your reflux, your reboard, you got better volatility. And that's a big optimizer. Okay. And so a lot of people do it manually. The operators do it. What happens during winter? They run the column at lower pressure than during summertime, and that's it. But you can automate it and take advantage of differences, not just between winter and summer, but also between day and night. Whatever it is, this is an optimizing control and one that's very slow. Now, how does it work? What you see here is what we saw before. This is just a normal pressure control with a valve in the vapor overhead. Now, one thing, and again, there's many ways of doing a floating pressure control. The one I'm going to show you was the one that was developed by a gentleman called Greg Shinsky, who's been one of the greats in distillation controls ever. And what he's doing is he's installing a valve position controller that looks at the position of the valve. Now, during summer, the valve is almost fully open. So say 70% open, 80% open, and he's going to keep it like that. So the valve opening is going to be the same as what he does during the wintertime, during the summertime. But then if it starts closing, which means you've got more room out there, he changes the set point on the pressure controller to keep it open again. In other words, he reduces the set point so you operate at lower pressure. And so this is what he does. And now this is a slow movement. You might do it over half an hour or something like that. So still the normal pressure control is fast and just like we said before, but over a period of time, it optimizes that. And the benefit of that is not just for going summer to winter and reducing energy, but in addition to that, keeping a lower pressure also keeps you away from the relief valve setting. And that's a big benefit too. Now, there might be some constraints. Of course, if you reduce the pressure too much, you might run into flooding in the column, or you might not be able to get rid of the bottom product. Okay, well, these constraints need to come into it. If you got computer control or even a DCS, you can work them in. But whatever it is, this is the principle. So with this beautiful method, might be a great time to conclude this presentation. So ladies and gentlemen, thank you for your attention, and I'm going to send it back to Sabrina to manage the questions.
Thank you, Henry. I think we have all feel a lot smarter now, and thank you for sharing your knowledge with us. So as a reminder to our audience, I'd like to let you know that you can submit your questions in the Q&A panel, and please address it to all panelists. So for our first question, back in one of the very first examples you had, Henry, there was a question about the control valve at grade. And so the question is, would tracing the line provide any benefit, or do you have to move the valve?
Benefit, definitely. But it's going to be a shortcut solution, just like any other shortcuts. If you get some entrainment out there, it's not going to do you any good. But from atmospheric condensation, yes, it's going to help you against that. So it's definitely going to give you some benefit. There's other shortcut solutions. You can have a pumping trap out there or something like that. But obviously, the best thing, what we would definitely recommend is to put the valve up high. But as I said, actually, when we talk about this method out here, this one's a bit more difficult. You talk about big lines because they're using these big lines too, also for startup and stuff like that. So these are big lines, and sometimes you really have to have them at grade. And because of that, you really need to go. Tracing might not be good enough for that. But the pumping trap and the kind of steam tracing of that, not steam tracing, steam trapping of that is definitely a good idea in this case.
Thank you, Henry. So next, we had a question. Can you comment on good practices for startup of a flooded condenser?
Oops. Well, again, it depends on the system. I have not seen the startup of a flooded condenser to be a problem at any time. Initially, you just generate a little bit of liquid out there, get the level up in the drum, and once you get the level up in the drum, the whole thing is going to start working. The one thing that as long as you don't run into too much subcooling, you might want to cut back on cooling during that startup to make sure that you don't get too much subcooling out there. But as long as you configure the right way, that should not be much of an issue. The other thing, if you are concerned, fill the drum up with liquid to start off with, and then you've got that line sealed. Once the line is sealed, then you don't have to worry about the very rapid condensation that can happen otherwise.
Thank you. For a flooded drum, can you not include an equalization line to the condenser and use it as a continuous vent system for non-condensable separated in the liquid full drum?
Run it by me again.
For a flooded drum,
yes.
Can you not include an equalization line to the condenser? And
there's no equalization line in that case. You do not need one.
Okay, but could you include it then?
Could you include it? Yeah. Wait.
And you use that as a continuous vent system for the non-condensables separated.
From the drum to the condenser, basically a line from here to this vent. I don't see any reason why not. Definitely a line from here to there. I think that's going to work quite nicely.
Okay.
Yeah, I think it. Again, I'm not sure, but it makes very good sense to me. Yes, if that's the intention. You don't need the, but if you want to use it, that's good.
Okay.
I want to make.
Take a moment to.
Yeah, I want to just think a little bit there.
Okay.
The only thing is I'm just wondering if backflow could be a problem in this case, and it can actually give you unflood the drum. I don't have any experience with that thing, but there's some tricky hydraulics in the system like that. So, I'm just wondering if you get that backflow that goes out here. Okay. And whether that can unflood, can unsettle the drum instead of doing what you want it to do, might do the opposite. Yeah.
But it probably requires a closer look.
It requires a closer look, absolutely. And I want to mention just how tricky it is. This is I'm going to skip to a slide that's let me just go. There's something and what I'm thinking of is an experience that we had. Hang on, that we had some times ago. Or not some times ago. This is an article that was published by a guy called Manny from. He was a Canadian. I can't remember exactly what company he worked for, but okay, that is the system that they had. And one problem is that they needed to have a relief valve out here, okay, and they put that relief valve up here again above the drum, and that relief valve was chattering all the time. And the reason is that you've got a vapor pocket out here, and that vapor pocket condenses and expands and all that. And as it does, it sucks some liquid in there, and whatever it was, and so in other words, the height of liquid out there goes up and down. And sometimes that liquid banged against the valve, so it was chattering and it was leaking and doing all sorts of things. The paper by Manny. I don't have the. If you look at my paper on flooded condensers, you'll find that reference to a paper by Manny. And really, if you want to talk about flooded drums and kind of get a good understanding of the hydraulics of that, take a look at it, because there's a lot of complicated hydraulics in that. So before you do any kind of lines out there, take a close look at Manny's papers. M-A-N-I. That was the way he spells his name. It was a classic, really was.
Well, thank you, Henry.
Okay.
I think they will do so. Okay, another question. Are there specific services that lend themselves to having the valve in the condenser inlet?
Um, the, as I said, there's some licensors that do it routinely. Just every time you get something from that licensor, they always put it in there. And hey, it's a good control system. The only trouble is the cost. The cost, both the operating and the capital. So as long as you don't mind and the one other system, yeah, one situation lends itself. That was a good one time is when you want to minimize subcooling. And I know some people that sometimes find subcooling undesirable. And yes, because of that, they prefer to do it in the inlet.
Thank you. So what are your thoughts about annotating PFDs with no pockets or self-draining as opposed to waiting until P&IDs are done?
Absolutely necessary. I'll tell you, let me tell you a little anecdote here. You know, believe it or not, remember when I told you that system is a big no-no? I've designed a system like that. Believe it? I designed a system like that. That was before I was joined Fluor, but it's nothing to do with the engineering contractor that I worked with. It was something to do with me. It was I take full responsibility. And in fact, well, I didn't design it like that. I designed it like this, right? But not exactly. I didn't have all this. I didn't have that valve. I didn't have that. But essentially, I designed that. The liquid was going to the liquid. The vapor was going to the vapor. And we left the P&I. And we had I did the PFD on that one. I did the P&ID. That time I was a process engineer and I was doing that with some background in distillation. And so I did that. There was a naphtha splitter. And that's it. And we finished. And the next thing, and everything was, then the client came, reviewed, everything was okay. That's it. They made a few changes and we just went ahead. And then next time I hear about it was a year later from the field. Hey, we can't keep a steady pressure in the column. I traveled to the field, take one look at it, says, wait a minute, that's not how I designed it. What happened? I designed a different way. Well, the way very often engineering companies work, and again, and I've seen that in many, is a lot of the time, the process engineers will do the P&Is and stuff like that, and then the client reviews it. Once we pass the review, that goes to the pipers. And then the pipers do it their way. Now, for the pipers, something like this and something like that is the same. And that saves money, so they do it like this. They try to help the client. They try to save money. And they don't feed back. We don't get a feedback for that. And next time we hear about it, it's in the field. And yeah, at that time I learned, you learn from your own experiences. And at that time I learned that you need to put these notes that you mentioned, they're must. Because, hey, if I put a note out there and say, look, that vapor needs to be connected to the vapor without any pockets, just like you said, liquid to the liquid, the pipers respect that. As long as the note is there, they will do exactly what the note says. But if the note is not there, it's open game, and they end up with stuff like that. So the answer is absolutely. These notes must be there.
It's good to know.
Yeah.
Okay. For the condensers, I grade the hot vapor bypass, which was slide 22. Could you comment on an appropriate sizing basis for the rate through the hot vapor bypass valve?
Yeah. The way to size that valve is consider how much vapor you need on a cold winter's day, because really the biggest heat sink that you've got is, well, both the subcooling, but even more so the ambient conditions. And people don't like to insulate these drums because of external corrosion concerns and stuff like that. If you got the drum insulated, that's really nice. But if the drum is not insulated, think cold, rainy day during the winter time. And at that time, you're going to get as much condensation as you're going to get. And you need to be able to put enough hot vapor out there to counter this plus the travel of cold from coming up. But don't forget that what's going to be very important is to make sure that the cold does not freely get up there. In other words, that you don't disturb that surface while you're doing that, because the minute you disturb the surface, you need a lot more vapor through that bypass. And in that case that I mentioned with Valero, which we had, it was incredible the amount of vapor that it needed, because that surface was suddenly, because they were lifting this cold, it was lifting that cold liquid to the surface. It opened the valve almost from something like about 5,000 pounds per hour to about 30,000 pounds per hour, and still couldn't keep up with it. So the key is this. Again, you keep out there, then all you have to worry is about a cold winter's day and counter that, and maybe put an over design factor on that, and you still end up with a valve that's not very big.
Thank you, Henry. So is the vent location important in condensers due to carbonic acid concerns?
Well, among other things, yeah, absolutely. Not just carbonic acid, it's just being able to vent the condensers. If you can't vent the condensers, you're going to inert blanket the condenser. You're going to lose heat transfer. So it's very important. Now, the good practice is to always put the vent in the place where the inerts accumulate. So just look at a condenser, look at where it does, and look for the place where they're going to accumulate. It's usually going to be on the top, but let's say if the entrance is out here, the vent is going to be at the end of the condenser. Now, if it comes in the middle of the condenser, you need a vent on each side. If it comes at one end of the condenser, comes out the other, then you only need a vent on one side. But whatever it is, look for the place where they're going to concentrate and follow that. And there's a very simple, very good technique that I would like to recommend to you. Once you look at the condenser, at the physical arrangement of the condenser, the drawing, whatever, imagine that you are a non-condensable molecule. And you're traveling through the condenser. Which way will you go? And go to the place where you're going to go and put the vent right there.
Okay. Thank you. So what about designing a hot vapor bypass while controlling the cooling water? What is the sizing basis of a hot vapor bypass and the suggested or typical control scheme?
Okay, the two don't usually go together. Okay, the only time, if you want to use the cooling water control that we mentioned before, like this, if you want if you want to use that method out there, that is only suitable when you got a vent gas. And if you got a vent gas, you don't want a hot vapor bypass. Hot vapor bypass is only for total condensing. So I would not marry the two of them together. So it's either or. If you've got total condensing, hot vapor bypass is definitely an option. But the minute you've got some vent gas, hot vapor bypass is not a good option.
Thank you. So Henry, do you ever see pressure control via dynamic tray elements and sensors along the column?
What do you mean by dynamic? The answer is no. Obviously, I don't see anything. The pressure control is usually, it's either at the top of the column, sometimes it's in the reflux drum, depending. If the pressure drop between the column and the reflux drum is not variable, you can put it on the reflux drum. Some people frown on it, but in some cases it's actually used, like, for example, we're going back to this system out there. That is a very common one for pressure. This one is very commonly controlled from the drum because of the vent gas, and the vent gas and the inerts, they come into here, they don't come upstream. But usually with something like that, you design it for kind of not a variable pressure drop. So basically the pressure drop in the column is kind of tracks the one, or tracks the one in the drum. So in this case, yes, but most of the time the good practice is to control it from the column rather than from the drum, and especially important if that line is undersized in this case. Now, incidentally, you've got a system like that, that line needs to be sized for self-venting flow, because you're going to get some vapor, you're going to get some liquid. You don't want to choke that line. So it needs to be sized big enough for that. And then you can put the drum, the pressure drop in the pressure control in the drum. If that line is not sized for self-venting flow, you can have liquid backing up and coming down, and you might have some fluctuations in this situation. But I haven't seen, I don't have any experience with some pressure from various points in the column. So it's either the top of the column or the overhead line or the drum.
Thank you. So with a higher degree of subcooling in flooded condensers, the internal reflux in the column does affect column pressure and the traffic inside the column. Have you seen any issues with that in distillation columns?
And we're talking about straight distillation. Whenever you've got subcooled liquid, what it will do as soon as it gets into the column, it will condense some of the vapor, and the internal reflux is going to be higher than the external reflux. I've seen problems when you've got some variability in it. And one thing that people do is what they call an internal reflux control. Now, what they do is essentially, instead of controlling on the external reflux, they control on the internal reflux. And you might say, well, what do they do? Do they put an orifice plate inside the column? The answer is no. What they do is they do a calculation. So what you do is you're going to take the flow rate of the reflux and realize the first thing is as it gets into the column, the subcooled reflux will condense some of the vapor and come to equilibrium. So you can actually calculate how much heat it needs to get to the boiling point, which is essentially the column overhead temperature minus the subcooled temperature, right? By the heat capacity, by the flow rate. And then when you divide by the latent heat, you know how much stuff it will condense when it comes to the column. You add it to the reflux, and this is your internal reflux control. And when you can do that, in this case, that can smooth a lot of fluctuations. I know this was, again, before I joined Fluor, we were doing some work with a refinery in Kuwait. We're doing a whole revamp on them. And one thing that their client told us is that they've got a big problem during wintertime because they get thunderstorms. And in Kuwait, water is at the premium, so everything is air condensing. And when these thunderstorms hit an air condenser, you know what it does to the pressure control. It just drives it crazy. And one thing that we've achieved, had a lot of success with, is by putting these internal reflux control loops on the columns. And so these are things that can help you out. And so normally you should not see a problem with that. Now, I want to take one exception to this. And the one exception where it might cause a problem is when you're dealing with multi-component distillation. There's some kind of this. I got a few columns in my unsolved mystery files on that, and for some reason, when you get a highly subcooled multi-component reflux, that can cause some. I believe it might be choking the upper downcomers when it does that. So that could be a problem. Also with packings, it could be a problem too, because with packings, it might lead to some maldistribution. But other than that, and in these cases, you might want to go with that control system that we mentioned before that reduces your subcooling. But normally, I'd say all these cases I mentioned are exceptions.
Okay, Henry, we have time for probably just one more question. So staying with the flooded condenser, would a seal leg in the drain line from a flooded condenser work?
That is something that's very commonly done when you don't have a drum. This is something that you do in specialty chemicals a lot. That's with that seal leg. Exactly that. You don't have a drum. You don't have a pump. That's how you eliminate the. That's how you eliminate the. That's how you eliminate the drum. And so the answer is yes, but it's usually not very suitable for large scale equipment. It's more suitable for the smaller operations, which is very typical of specialty chemicals. Yes, again, it needs to be engineered properly, and that's another story.
Okay. Well, Henry, that's all the time we have for questions. We do have many more questions in the queue. And so to our audience, yes, this is being recorded, and we will send out a summary of the questions and responses with the link to the video. So thank you, Henry. We appreciate all of you for attending today and for your questions. You've all been a very engaged audience, and it's been a pleasure being your moderator. So next, we will be hosting our next webinar on Thursday, November 19th at 10 a.m. Central Time. And in this webinar, subject matter expert Stephen Prevett will talk about data-minded decision-making. This presentation will be an overview of common industrial tools to accomplish statistical process control in conjunction with Pareto charts and histograms. Actual project examples will be shown, and you will be provided the means to apply these tools to your leading and lagging indicators. So please keep in touch with your Fluor contacts follow our social media postings, or head to the Innovation Builders page on fluor.com to register for future webinars. We appreciate your attention today, and thank you for joining. We will send out a compiled list of the Q&As within a few days, and we will notify you when the webinar recording is available on fluor.com. If you have any additional questions or require additional information, please email innovation.builders@fluor.com and someone will get back to you. From all of us and the Innovation Builders team, have a safe day. Thank you for joining us.